Hello and welcome back to my channel, where the goal is to provide simple and correct arguments in calculus. Today we will prove that the harmonic series, so the summation from n equal 1 to infinity of 1 over n, diverges. This is used in calculus and it is often shown using integrals. However, the proof of the divergence of this series is actually very simple, quite elementary, and there is no reason to use something as complicated as the integrals. This is the first part of a series of 2 videos. In the next one, we will show that if we change this series to the series of 1 over n to some power s when s is greater than 1, then that series actually converges. So let's get to it. Let's begin with the harmonic series, and let's first write out what it actually is. So it is the sum of the following numbers, the reciprocals of consecutive natural numbers, and so on. The key to showing that the series diverges is to rewrite the sum, or rather group the elements in the sum in a particular way. So we're going to do the following. We're going to leave 1 by itself, and then plus 1/2 also by itself, and then plus 1/3 and 1/4 will be grouped together, and the next group will be 1/5, 1/6, 1/7, and 1/8. The next group, everything from 1/9 all the way to 1 over 16, then everything from 1 over 17 all the way to 1 over 32, and so on. As you can see, there's a certain method to this grouping. That is, the last term in each group is 1 over a power of 2. So now observe that we can write certain inequalities for each of these groups. So 1 is certainly greater than or equal to itself, and 1/2 as well. But 1/3 and 1/4 are both greater than or equal than 1/4. So I get 2 times 1/4 here. 1/3 plus 1/4 is certainly greater than 2 times 1/4. Now in the next group, every fraction is greater than or equal than 1/8. So the entire sum is greater than or equal than 4 times 1/8. In the next group, every fraction is greater than or equal than 1/16. So the sum of them, and there are 8 terms here, is greater than or equal than 8 times 1/16. Similarly, in the next group, there are 16 terms here, and each of them is greater than 1 over 32. If you see, the idea of grouping the terms this way is that each of these numbers on the right-hand side is actually equal to 1/2. And so it should already be intuitively clear that I can always gather enough terms from the harmonic series to exceed the next 1/2. I already, by summing all the terms up to 1 over 32, have exceeded the number 1 plus 1/2 plus 1/2, that's 2, plus 1/2 plus 1/2, that's 3, plus 1/2, so 3.5. If I want to exceed 4, I'm going to add the next terms, 1 over 33 all the way to 1 over 64, and this way I exceed 4. Then if I add all the terms from 1 over 65 to 1 over 128, I will exceed 4.5, and so on. It's pretty clear that there is no bound to this process. So that means the harmonic series, or the partial sums of the harmonic series, exceed every number. To be a little bit more precise, or to make this argument a little bit more precise, let's just look at the following partial sum. So I am going to say, let n be a positive integer. And we will look at the partial sum as sub 2 to the n, which is just the sum from n equal 1 to 2 to the n of 1 over n. Now I can use the arguments we just made to estimate this partial sum. Because if you see, just taking 1, that's of course the partial sum with just one element, so that's 2 to the 0. Taking the first 2 gives me partial sum S2, so that's S2 to the 1. Taking the first three groups, that is 4 elements, 1, 1/2, 1/3, and 1/4, so that's S4, or in other words, S2 squared. And I can continue this way, so taking the next group will give me 8 elements, so that's 8S2 to the 3rd, and so on. Now I can see a pattern for bounds for these partial sums. Namely, let's see, so S1 is greater than or equal than 1. S2, so 2 to the 1, is greater than or equal than 1 plus 1/2. S2 squared is greater than or equal than 1 plus 2 times 1/2. S2 cubed is greater than or equal than 1 plus 3 times 1/2. S2 to the 4th, so this is the sum all the way to 1 over 16, is greater than or equal than 1 plus 4 times 1/2. Because we have 1 and then 4 1/2s, and so on. So if you now see the pattern is here, this exponent is always equal to that number that multiplies 1/2 on the other side. So from this we get that S2 to the n is always greater than or equal than 1 plus n times 1/2. So we conclude that we have S2 to the n greater than or equal than 1 plus n over 2. And if we take, therefore, if we take the limit as n goes to infinity of S2 to the n, we get that this is greater than or equal than the limit as n goes to infinity of 1 plus n over 2. But of course this sequence here diverges as n goes to infinity. The sequence goes to infinity. So this limit here is infinite. So we have proven now formally that the limit of partial sums of the harmonic series is greater than or equal than the limit of this sequence, which diverges. Therefore, the harmonic series diverges.